From this lecture, we will start the study of electrostatics. So let's see what is electrostatics. So this word is made of two words, electro and statics. Electro means electricity and statics means stationary. So as this word suggests, in this electrostatics, we will study the effects which are caused by the charges at rest. So in this, we will study the electric field created by the charges which are not moving. And since current is made of movement of charges, so and magnetic field is created by the current. So in our study, we will not come across magnetic fields. So while we will study this electrostatics, magnetic fields will not come into picture. But we will think that this is very simple topic, then why are we going to study this? So the importance of this topic, although it may be the simplest topics in the subject, but there are many phenomena which are explained with the help of electrostatics only, like lightning, the thunder and lightning, especially lightning, not the thunder is just the sound. The lightning phenomena is electrostatics majorly in its nature. Similarly, there are phenomena like St. Elmo's fire. There are so many YouTube videos of various pilots showing St. Elmo's fire. Similarly, in arid regions where humidity is very low and where flour mills or grain storage mills or plants, they may face some kind of fire which are usually called grain dust fire, which are caused by the spark created by electrostatics only. So there are so many things for which electrostatics is important. Now there are many applications like Xerox machines, inkjet printers. They all work on the principle of electrostatics. So even though it is a very simple subject, but we should understand that there are so many things which are just dependent on electrostatics only. So where do we start? As usual, we will see the most basic law governing electrostatics. So the law is Coulomb's law. Why this is called a law or postulate? Although it was discovered by Coulomb experimentally in his lab, however, the expression which he gave is taken as a law, means it is a fact of nature. What does it say? It says that, let us say there are 2 point charges Q1, Q2, and the point charges, although are theoretical concept where we assume that they are having negligible size or zero size, which is practically not possible. However, if the charges are so small as compared to their separation d, then we can consider them as point charges. So what Coulomb said, he said that the force on charge 2 due to charge 1 is given by some proportionality constant k, q1, q2, that is the magnitude of these two charges, and this distance d squared, and the force direction will be in the direction of the unit vector a12, means from 1 to 2. So a12 is in this direction. So this is the force by charge 1 on 2. So as we can see, if Q1 and Q2 are of same sign, means Q1 is positive and Q2 is positive. So what does it say? It says that F12 will be positive, means the force on Q2 due to the charge Q1 will be on the right hand side, means it will repel. Similarly, force by 2 on 1 will be in this direction and it will be also repelling. So in this way we see that the same charges, same sign charge or sign having the sign same, have a force which repel each other. However, if one of the charges is of opposite sign, let us say Q1 is positive and Q2 is negative. So what will happen? This F12 will be of negative sign. So the direction will be on the left hand side. So you see that the charge Q1 is going to attract the charge Q2 instead of repelling it. So in this equation, this is a vector equation, we have both information, the magnitude of this force as well as the direction of the force. So although this law was discovered in a lab, so we can expect that the at the time in 1800s, some year of 1800, the accuracy of the experiment may not be that great. However, it was the ingenuity of the Coulomb that he got the idea that this law is having some inverse square proportionality. Okay, so for SI units, this force in normal vacuum is given by 4 pi epsilon Q1 Q2 over R square, and the direction is from 1 to 2. So this is the force by 1 on charge 2. This is the Coulomb's law. Now, what will happen if these two are not point charges? Let us say one of them is a point charge and another one is a distribution, a uniform distribution of charges. Let us say the charge density means Coulomb per unit volume is given. So how to do that? Such kind of scenario we will see later on, but for that we should know that this Coulomb's law follows superposition. So what does it mean? As far as we can see that this force expression, force by charge 1 on 2, is given by some proportionality constant Q1 Q2 over R square. So we see that force on Q2 is just proportional to the charge, or this is a linear equation as far as this charge is concerned. So we can see that this force will follow superposition principle. So what does it mean? It means that let us say this charge Q2 is there, and however we already have charge Q0, Q1 and Q3 at some random places. So we want to find the total force on this charge. So what we will do? We will use Coulomb's law. We will find F02 means force on charge 2 due to Q0. Similarly, we will find F12. We will find F13, and then we will add them vectorially to find the total force on charge 2, which will be F02 plus F12 plus F13. So this basically sums up electrostatics if we are able to find so many things. However, we will find that this is a little difficult concept to understand. First of all, we don't know whether this action thing happens immediately. How does the charge know whether already there is some other charge placed somewhere? So the scientists have devised a thing called electric field. As we already discussed in our previous lectures, the meaning of vector field and scalar field. So electric field is a scalar field and it is given by electric field at point P is found by this equation. The force on a test charge which is placed at point P, and this is the test charge. When this test charge is so small, its magnitude is so small that it does not affect the distribution of other charges. So what does it want to say? It says that, let us say there are already n charges, q1, q2, q3, q and so on, and we want to find an expression of electric field at point P. So let us say this is point P. Now we want to find the electric field at this point. What does it mean? It means that what we will do, we will bring a very small charge QP, a test charge QP, and its magnitude will be so small that the bringing of this charge will not affect their position and they will stay on their positions. Okay, so when it happens, we will measure the force here on this test charge and we will divide the total force by the magnitude of the test charge. This will give us the field at point P. Similarly, we can find field at so many other points. So you see, this field will be a function of the position. So this is a vector field, and at every point this force is going to have a direction. So this is going to be a vector field. Now, although this electric field is a theoretical concept which was formed to explain the action at a distance thing, however, it is quite real in nature. What does it mean? It means that we will study later that this electric field carries with it an energy, and the energy density is given by half epsilon naught E square, where epsilon naught, which we have seen in our previous slide, is a proportionality constant or the constant of the material, and here it refers to the vacuum, the permittivity of space. So you see that this field is carrying with it a charge, this energy density of this much, so it is having some physical sense in itself. So it is just not a purely imaginary or theoretical concept. It really has some physical meaning. Now we want to explain further that this 1 by r square, how do we know that this is perfectly 2? It is not some 1.9999999 something. We will see later on so many things like Gauss law and its application, and from that we will find it is truly r square and not some 1.99, and it has been measured experimentally also, and its accuracy is more than 1 in 10 raised to power 15. However, we should know that this Coulomb's law starts to give wrong results when we go below 10 raised to power minus 14 centimeter scales. So it is found that the force measured in this scale is about 1 by 10th of the force calculated through Coulomb's law. So either this Coulomb's law breaks at this level or there is something else which comes into picture. So scientists are believing that it is some pions or mesons, and some charge is smeared on proton, and so many other things, which is a study of higher classes. So we will not go further, but we should know that the Coulomb's law starts to give incorrect results when we go below a certain level. However, in our normal studies, we will not go beyond some molecular levels. So our Coulomb's law and other laws are perfectly valid in that sense. Now this is something in which we have seen the vectorial equation of Coulomb's law. Now let us solve an example how to use this Coulomb's law to solve some very simple problems. So let's see. Let us say there are two charges, Q1, Q2, and it is having 8 Coulomb and it is having -2 Coulomb. It is purely imaginary because Coulomb is a very big unit, and we will be fortunate if we find some micro Coulomb somewhere. Okay, so Coulomb in its sense is a very big unit. So let us say these two charges are separated by a distance of, let us say, 20 centimeter. It is a purely artificial problem, so we have to just see the concept only. So we want to see whether there is any point where there will be some equilibrium if I place some charge. Let us say there is some charge Q which I have to place on this line. Is there any point on this line where this charge Q will not face any force? However, we will see in our future lectures that no electrostatic field is going to have a stable equilibrium point. No electrostatic field has a stable equilibrium point. There will be so many equilibrium points, but a stable equilibrium point will not be available except exactly on top of another opposite charge. Except on top of another opposite charge. And this is a theorem which is actually known as Earnshaw's theorem. We will prove it after we study Gauss law, why there is no stable equilibrium point in an electrostatic field. However, let us now solve this problem. So we want to see whether the point is going to lie between this or not between these two charges. So we are trying to find a place where the forces due to these two charges are in opposite directions. So this is a negative charge. It is going to attract this positive charge, and this is a positive charge. It is going to repel this positive charge like this. So we see that if an equilibrium point exists, it will exist here on this side of the RHS. Let us see whether it can exist on this side or not. Let us say at this point. So this will repel here, and this charge is going to attract here. So it may be possible that there is a fair equilibrium point available here. So let us try to solve this here. Let us say this is the equilibrium point and it is at, let us say, x distance from Q2. So the total force at this point P on this test charge will be proportional to Q1 4 pi epsilon naught. This is QP, let us say QP, and this is 20 centimeter plus x centimeter squared. I am not going to bother about the units. However, you should try to solve with proper units. And the force due to Q2 will be Q2 QP 4 pi epsilon naught x squared. So it should be total equal to 0. That is, the total force should be 0. So now let us see what happens? This 4 pi epsilon naught goes. Similarly, this QP goes. So in this sense, you see, QP is not going to come into our picture for calculation. So Q1 over 20 plus x squared should be equal to Q2 over x squared. Now we see units are not going to matter much because both will cancel out, the units will cancel out. So we see that x square by what is this thing, Q2 is 2 and 20 plus x square by 8. So 2 4s. So 4x squared is equal to 400 plus x squared plus 40x. So it will give 3x squared plus 40x minus 40x minus 400 equal to 0. So on solving, we can find x to be minus b plus minus b square minus 4ac upon 2a. So in this way, we can find the value of x, and we can find whether this x is positive. If this x is positive, the point will be here, and if x is negative, it means point will be somewhere here. So in this way, we can solve various problems by using Coulomb's law. Now in our next lecture, we will study about Gauss law and electric field in little detail. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel. And we have made a Telegram group for doubt discussion, and the description gives the link of the Telegram group. Thank you.